deform plastic?
Yeah. Right on time. All right, any questions before we get started? So of course, just a reminder, midterm next Thursday. And so of course, we'll review on Tuesday. And so on, any questions about anything we talked about Tuesday? And so I was looking over the chapter again, and I realized in my notes, I think I was jumping ahead. So all that galvanic cell stuff is going to be after the midterm. So we're going to go back and do some things that are in the book, and then go over some homework. But I do have some handouts that are handy for today's lab, and then take us into next week. So there's an activity series of metals handout. And so this will be super relevant for lab today. And it kind of at least gives you a gist of what's going on. But essentially with this one, more reactive elements are at the top, and then you'll kind of verify this during lab. So you may want to grab that. But then today's lab will start leading us into the cell potentials and how those half reactions work. And so if you wanted to at least just grab this to kind of compare to the activity series, and then take you into next week, it's there as well. Then I have the lab printed out. All right, so let's go back in our textbook. Oops. And so we need to look at determining oxidation states in more depth. So how to do that, especially for organic compounds. And so let's kind of warm up with easier examples. So see if you can determine the oxidation state for these few species. And you could also practice your Vesper theory, drawing them out. So what do we get for the oxidation state of titanium for A? I hear a 4 plus. Did other people get that? So I see some nods there. And just kind of a refresher. So I'm just going to sketch out our Vesper structure. So we kind of remember, oh yeah, these types of compounds, 6 things attached to it, going to be octahedral. I'll put our overall -2 charge on there. And if we're being proper, we'll fill in all those electrons. Excellent. What about vanadium in this one here? What's its oxidation state? So +5. I see thumbs up for +5. So +5. So this one had an extra 1+ charge, and of course, oxygen is always -2. What did we draw a structure for that by any chance? Take a minute or so to draw a structure, maybe catch up on the other ones. You wouldn't add like a hydrogen.
So we're just missing an electron then?
Does anyone have what the geometry would be then for the structure, once you drew it out?
All of that. Two groups. Oh, just linear? No. It's bent?
Yeah. It should be linear.
The extra,
Oh.
the sheared off electron.
Yeah.
Same.
Yeah, well, I think it one too many electrons. That looks good. Okay. Yeah, it looks like we need at least a little refresher on this topic. So always good to revisit this. So remember, the key point is how many total electrons are in this party. And then, where's my periodic table? I'll just pull up another periodic table. So we have our periodic table. So vanadium here, right, has 5 total electrons here, so from the 4s and then the 3d. So it brings 5 to the party. So 5. Each oxygen, right, brings 6. So times 2 is 12. But then with that plus charge, you have to subtract an electron. And so that should get you to 16 total in there. And then I saw a lot of good starts. So you could just start, drawing a line to each one. Maybe you fill in, well, what if we do the octet here? So remember, you don't have to draw a correct structure right away.
Would the oxygens not be bonded or double bonded?
Well, we're getting there, right? So then you count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then someone was saying, well, maybe the oxygen should be double bonded, trying to get vanadium 8 electrons. So if we do that, so again, my other tip to you is you don't have to start correct, but okay, let's redraw that structure now. And so in the end, you should have gotten something that looked like this with double bonded on oxygen. And I thought this was a cool structure just because it's nice and linear there. And then we should put our plus charge on there. Excellent. So remember, play with your structures. Don't be scared to draw stuff. Play with it. All right, let's try these last two. So I'll give you all another minute or so. Find the oxidation state and then practice drawing your structures out. Little refresher.
So vanadium brings 5, so that's just trigonal pyramidal. Is it trigonal pyramidal?
Yeah. Yeah.
Minus 2 makes it plus. The other minus 2 brings 2. So it's going to make 1, 2, 4. That's also going to be true. Both, right? No? Okay, so 2 electrons.
Oh,
Okay.
I think I said the wrong thing for the first one.
Is it not trigonal pyramidal?
Yeah.
Yeah.
I think you have a shape right, just the name wrong, because they're the same shape.
that's what she said, is that you.
Yeah, so
they
that's
don't-
I said trailing. Oh, no, sure. It's where it's got like a lone pair
Yeah,
on the top, and then, okay, so that's tetrahedral?
yeah, I think so, hang on. I have
So then,
this.
yeah, I got it right. Cool. I just got the name. That's right, so it's tetrahedral.
Yes, tetrahedral.
It's
So long since I've seen it. Literally been a year and a half.
Did you not, were you not able to take the last quarter of last year?
Yeah.
But it's good practice.
What's your major?
This is good. You guys don't know.
I mean, yeah,
You
the
know,
other way to see
associate
it
with art just happens to be
yeah,
the
it's all on
for
there.
failure.
Designated two charges and then.
Is it MDA? Emerging Media and Digital Arts?
No.
All right, let's hear what you got for C. I saw some decent structures. So what should it look like? So I heard tetrahedral. And if we do that, I'll start with something. Looks something like this. And then are there any double bonds or anything? Or? So yes, oxygen should have a double bond. So if you could have started with oxygen without a double bond first, but then if you did your kind of formal charge analysis, you would have gotten formal charges on oxygen and vanadium, and that would be a hint to maybe add a double bond. And I can draw. So if you got to here, and you can still draw this out as one of those structures, because you could argue, well, you know, vanadium's hypervalent, but we want to minimize formal charges, so that's kind of the best option, as long as your metal can go hypervalent and transition metal, so it's fine being hypervalent. So if you had done your analysis here, so your formal charge on oxygen would end up being -1, vanadium is +1, so that's kind of your hint to move that to the double bond here. Yeah?
So I was a little confused on how do you choose which one goes in the middle of which element goes in the middle of the structure?
It's usually like which one's the least electronegative goes in the center, but then also like if you see a metal, usually it's going to go in the center.
They're just tend to be less electronegative.
Yeah, and they want to give up and donate electrons, so. And then what's the oxidation state of vanadium?
It is +5.
So +5, and so you could have gotten that, so -2 on oxygen, and of course each one of those chlorines is -1. This was overall neutral, so +5. And then what about this last one? Yeah, what'd you get?
I got +6 on the chromium and -2 on oxygen.
So +6 and -2, so that looks good. And then what did your structure roughly look like, or?
Is it double bonded everywhere? That's my question.
So let's do the analysis so we can figure out, well, how many double bonds? Well, first of all, how many electrons do we have total in here? So chromium is 6, so it brings 6 electrons to the party. Each oxygen brings 6.
32.
And then, yeah, the -2 charge. So 32 electrons. And so you could have started out just drawing, you know, a bond to each oxygen, fill it in. So this is one possible structure. But then what are the formal charges on it?
A bunch of -1s.
So these are all -1s, but then what's the chromium?
+2.
Yeah, so +2. So this kind of answers your question on how many double bonds we should have. So probably the best structure so that we don't give then chromium like a negative formal charge is just to make 2 double bonds. And it doesn't matter which ones you pick. And obviously you can go crazy drawing resonance structures then. So I'll just redraw.
Now would it be a +2, right? So it's the whole thing with +2 if we double bonded everything.
And then obviously make resonance structures if you want. Put your formal charges on whatever oxygen is carrying the negative charge. Yeah, so that looks good. So this was a pretty good structure, and then any of these resonance structures. Now let's see, we already answered oxidation state. Excellent. So we feel good about the metals at least, right? So now let's try organic structures. So we don't generally do organic structures. But let's just start with simple methane. And so kind of the rule that we've been applying as we pull apart our metal structures. So if we go back in another way to determine our oxidation states is to just give all the electrons to the most electronegative atom, and then you can compare to how many electrons it should have, and that also gives you the oxidation state. And so let's compare. And so now give electrons to most electronegative. So in this case, we could just redraw it. And so if all the electrons then in these bonds go to carbon, because carbon is slightly more electronegative, so that leaves us with kind of this
Methane?
little structure here. And then just like we do with the formal charges, we can analyze each one. So you take, right, your number of electrons in the neutral and then subtract it from however many are on there from our kind of pulled off structure. So of course for each one of these hydrogens, that gives you a 1+. Since it should have 1 in the neutral, it has 0 on it right now. So there's your oxidation state of hydrogen. And then of course, just recall back to your rules, right? Hydrogen is usually 1+ unless we're talking about metal hydrides, so that all matches up as well. That makes sense. And then so for carbon now, well, it has 8 electrons on there. So it should have 4 in the neutral, -8. And so that gives us a formally -4 oxidation state for carbon here. And then of course, your organic compound, the oxidation state should still add up to whatever it is. So of course, neutral methane, all that should add up to 0. So then let's look at other cases. So if you have this molecule, and we're just focusing on this carbon over here. So if it's next to another carbon, that doesn't affect its oxidation state. So you can either just kind of split that evenly, so give each carbon 1 electron since they're the same electronegativity. So then if we split that up, we'd get something that looks like this. Once again, all those hydrogens are 1+. And of course, you can start realizing, okay, hydrogen, I can always assign 1+, and then the carbon, if it's connected to those hydrogens, then it has to be, in this case, -3 to balance out those hydrogens, and again, that carbon doesn't change its oxidation state. And so the math works out, so 1, 2, 3, 4, 5, 6, 7, so 7, or 4 minus 7, excuse me, gives you -3 oxidation state. Questions about that one? So let's practice another one, or look at another scenario. So we have carbon, double bonded oxygen, and let's just put a hydrogen, a carbon on here for now. And so we're only focusing on this carbon. So see if you can pull off the electrons like we said. So give the electrons to the most electronegative atom, and we'll see what we get for oxidation states. So is this what we got when we pulled them off? So if we look at this, carbon is more electronegative than hydrogen, so it got those 2 electrons in the bond. We had a CC bond, so I just gave it 1 since we split that evenly. And then our oxygen is more electronegative than carbon, so we have 4 electrons in that bond. And then don't forget the lone pairs, I didn't explicitly draw them than I did in our analysis, so then it has 8 total in our kind of split here. And so what do we get for the oxidation state? Let's start of oxygen. So go back to your formula, right? So how many electrons are in the neutral oxygen? Yeah, the answer is -2. So you got that right, 6 in the neutral minus 8 on this little structure here. So exactly -2. And that matches what we expect for oxygen. It should be -2. That's unless it was a peroxide structure. And then, so what's going to be hydrogen?
+1.
So +1. And then what's carbon now? And so +1. Exactly. So we have 4 from the neutral minus 3. And so that gives us +1. And then double check yourself, does that match? And yes, so we have -2, +1, +1, so that gives us 0. Questions about this one? let's do another one. So what if this was a carboxylic acid group instead? So still double bonded oxygen, but now we have an alcohol on there. Let's see how your analysis went. So carbon, so CC bond again, 1 electron. Now our hydroxide, so right, oxygen is more electronegative than carbon, so it got those electrons, and it already had 2. And so oxygen, so same thing. And so now let's start with oxygen. So what's our oxidation state? So -2. And then, so this, right, we know our hydroxide has an overall -1 charge, so we could leave it like that and just say, okay, the hydroxide -1, or of course we could split that further, so you know oxygen is -2, hydrogen would end up being +1, and then what is on our carbon? What's our charge? Plus, what did you say at the end?
+3.
+3, exactly. So there's 2 ways to get that. We could do, right, just do the math. So 4 in the neutral. Now there's only 1 on there, so that gives us a 3+. And then double check yourself. So we said oxygen was -2, and then we can just leave the hydroxide as -1 as a group, since that's what it adds to. So that's -3. Since this is all neutral, yes, that has to be +3. All right, let's try a few more practice problems of let's see, so this nitrogen one looks funny. And it should have a -1 charge. So what's the oxidation state for the nitrogen and these oxygens? try this one. Question or?
Oh, I had the answer for the first one.
So let's at least, so tell me, where did you put the electrons then on your analysis? And then we'll,
I had all the electrons being taken by the oxygens, so nitrogen had no electrons.
so that looks good. So did everybody do that? So oxygen's more electronegative than our nitrogen, so they all ended up there. And so what do we get then for our oxidation state? Let's start with nitrogen.
Since all the oxygens are -2,
And then don't forget it has a -1 charge.
since it's a -1 charge, it would be an oxidation state of +4.
+4 or plus?
Oh, +6.
Oh, try again. Because, yeah, 5.
Yeah, 5, that's what, okay. I was tripping myself up.
So remember, right, nitrogen has 5 in the neutral, so 5 minus 0 gives us to our answer. Or you started with the -2, so each oxygen is -2, times 3 is -6, but then we said this was a charged compound, so +5. Excellent. And so try this one, and I was trying to make it clear. So this one also has a -1 charge on it, so it's sitting on the nitrogen. Do you need another minute or so for analysis, or? Okay, I'll give y'all more time. So tell me then, between carbon and sulfur, who gets the electrons?
Sulfur and
Sulfur, so I heard a lot of sulfurs around the room. And then what about nitrogen? So nitrogen, I saw that again around the room. So let's start with, let's do carbon, because it looks easy. So what's our oxidation state of carbon?
+4.
So +4, and then sulfur, -2, and then nitrogen, so -3. And so that worked out with the math, so 5 minus 8 is -3. Sulfur looks just like oxygen, so we kind of expected it to be -2, and then everything adds back up to overall -1. Excellent. Questions? All right, we're going to do one more example of this type of problem, and we'll take a few minutes for it. So once I draw it out, you can ask your partner or your neighbor, try to figure it out. And I'm going to draw it explicitly out.
What are you making?
M-nitrotoluene.
Okay.
So yes, find the oxidation state of all those atoms.
0, 0, 0, 0.
Oh, and I forgot hydrogen right there. There we go.
So, what do you mean by neutral? So it's all zero charge.
Yeah, all those are 0 charge. And so is this one. It's top 4. That one's 4. So is this one. This nitrogen, it could be -3 or
Wait, hold on.
+3.
Are we taking into account that we're like is carbon is more electronegative than hydrogen, right? So it should take those.
Yeah,
So
but it's neutralized. It doesn't have the difference. So the hydrogen.
I don't think that makes sense.
Well, then this shouldn't affect your answer. I realize I just left out the double bond between those carbon,
Oh,
so that probably helps. Sorry.
okay.
Do we want to start going over some of these? So let's start with maybe this top group over here. What did you get for the hydrogens, their oxidation states, or?
They're all plus ones.
So all +1. And then, so this bond doesn't affect our carbon. And then, so what's our oxidation state of carbon here?
It's going to be -3.
So -3. And then, let's see, what do we get? So what about this carbon? What do you notice about this one?
It's neutral.
So it's neutral, so it's bonded to all carbons, and so it end up splitting every bond. And so that gives you 4. So 4 minus 4, 0. Oops. And let's see, it
The
doesn't.
nitrogen is what messed me up. I'm not sure what it is.
Yeah, we'll get to the nitrogen. What about this carbon here?
But it's not double nitrogen.
-1, exactly. So it's bonded to that hydrogen.
So it's
Otherwise, then it's neutral. And what about the carbon across from it? Yes, excellent.
That's what, I don't know what to do with that.
And then you have, so 1 plus again on this hydrogen, -1, so this is kind of repetitive. And then, so let's look at this part in more detail, and we can even do our analysis. So we have, I'll just draw this part. So we have a carbon, another carbon, and of course also our nitrogen. So starting with this, so we do our analysis, we can take our carbon, of course it gets 1 from there, 2 from our double bond, but then which one's more electronegative, carbon or nitrogen? So nitrogen takes those 2 electrons from the bond, and then now, which one's more electronegative though, nitrogen or oxygen?
Oxygen.
Oxygen. So now oxygen takes all these. And so we get something that looks like this for our analysis. And so let's start with the oxygens. So what's our oxygen oxidation state? So -2, -2. And then if we do the math on our nitrogen, so +3, so 5 minus 2, +3, and then what is carbon? So +1. So that was a little tricky there, so I'll write that 1 plus, 3 plus. And then hydrogen, 1 plus. And of course, you can double check yourself, add them all up again, and it should be 0. Questions about this? We feeling okay? So this will probably show up on your midterm, unless Dorothy wants to exit, but we'll see what the final version of your midterm has.
Are we doing review on Tuesday?
Yes.
If it's bonding like with like, they're just gonna split it, so that, but, just because of the structure, this has 2 lone pairs, it has 2 bonds, so when oxygen, since oxygen is electronegative, it's gonna.
So the last part we're gonna do is like the stoichiometry, just because it's like review.
But this one, it already has 3.
I'm trying to find your book problem.
2 here, so when, and it's also electronegative, so instead of taking 4, so instead of taking the 4, like this oxygen, it's just gonna take the 2 because it only has a single one. So it's not, this is the structure you're given, you're just following the rule of this is less electronegative than this, so it's taking. So it takes those 2. Then this only has that.
So we're just basically the bonds.
Yeah.
All right, so let's just review the stoichiometry part. And it should feel like you know it, but let's just go through it so we all know that we're on the same page and everything. And so right now, I'm just doing your book example. We can do the homework too. And so it's just starting off by giving us a scenario that the concentration of ozone in some air can be determined by reacting the ozone with some sort of potassium iodide solution. So they just showed the relevant half reaction there. And so that makes O2, and then oxidizes the iodine to the I3 species. So it's according to this reaction. And so then the concentration is determined by titrating the sodium thiosulfate with the iodine here. And so that reaction is given. And again, they're just showing you the relevant ions. So our sodium thiosulfate is just given as 2 equivalents of thiosulfate. plus our new iodide species to give us this species, tetrathionate, plus our iodine back out. And so now here's the problem. Let's see if I can. So again, this is just from the book. I didn't want to write it with my handwriting. So now we have a 50 ml sample of our potassium iodide. It reacted with 43.15 gram sample of air. And so now if 54.56 milliliters of a 0.002475 molar solution of sodium thiosulfide are required to titrate, we have to figure out the mass percentage of ozone. And again, you should have been able to do this with your stoichiometry skills from second quarter, but we'll go through it since it's a lot of steps. So what do you think the first step is, just looking at this? What do we need to calculate?
So first we need to figure a way to add these two chemical equations together, correct?
We don't really need to add them. We just see kind of what we need. And so we're given at least the molar amount of our thiosulfate, right? We could calculate that. We're given milliliters, we're given molarity. So we can easily find moles. I'm going to say we're essentially given moles here. But we want to figure out is at least mass percentage of ozone. So then we just have to use these two equations to figure out, well, if I can solve moles of this reactant, then that gives me how much iodide species I had, right? They're in a 2-to-1 ratio. And then if we go back and figure out how many moles of that, that's the same as how many moles of ozone were in our sample here.
So it's just 2 to 1.
Yeah, so just a 2-to-1 from there. And so let's start with that. So just walking through those steps. And so I'll just write it out. And actually I'll change this, so this is moles per liter, just using dimensional analysis. So I'll say find moles of our thiosulfate species. So did we get this answer? So 8.5 times 10 to the negative 5th moles. I see some nods. And then again, just use our ratio. We want to figure out our I3 concentration, which is equal to our ozone. And so we could set something up like that. So I want moles of iodine. So I have 8.55 times 10 to the negative 5th moles of S2O3. yeah, divided by 2. So I'll just put it for every 1 mole of iodide, we need 2 of S2O3. So then we just half it.
4.27. If it's 4.275, should we round up to 2.8? Or 4.2?
Oh, yeah, I just wasn't paying too much attention. So 4.728 roughly moles. Try not to round till the end. And so that's a 1-to-1 ratio. So you can just say I3 is equal to ozone moles. Again, from our other equation. So that's why we needed both of them. And so we still have this many moles then of ozone. And so now we can figure out the mass of ozone. So what's 16 times 3? 48, right? So 48 grams per mole for our mass of oxygen. So find grams in our sample. So we get like 2 milligrams. And then to answer the question, so it said calculate the mass percentage of ozone in our original 43.15 gram sample. So we can just divide that. And then, of course, multiply it by 100. And so 0.004%. So pretty small, but I wouldn't expect there to be a large amount of ozone. So questions about that one? Are there questions on the homework, or what do we need to do practice on? More like organic structures and oxidation states? More stoichiometry review?
Do we have a quiz in ST23?
Yeah, we'll have our quiz today. Trying to find your homework, but I don't know where I put it. Oh, there it is. Let's see, so we have balancing equations. You could practice more of the titration. It's just whatever you're feeling like you need the most practice on. Do you want to do 6 or 7 then from the homework? Okay, see if we can do both then. So let's look at 6. So we have the amount of iron 2+ in some unknown sample can be determined by titration with a standard solution of our permanganate according to the following equation. And so the endpoint is indicated by this persistent purple color. And so if you titrated a 2.5 gram sample of iron ore, and it's completely dissolved in aqueous sulfuric acid, and titrated to an endpoint with 22.75 milliliters of a 0.1015 molar permanganate solution, what is the mass percentage of iron in that ore? So at least take a minute or two to think about it, and we'll go over it.
Is this in our most recent homework?
Yeah, so it should be in that packet.
Yeah.
2.5 aqueous sulfuric acid. Where's this one? So they're not showing us the whole formulas. Is that H plus the sulfuric acid?
No, because it's dissolved first.
They just didn't want the bystanders then.
So how should we start this one? Let's do it. So let's find moles of permanganate, and they gave us everything we need. So we have milliliters, we have molarity. So I'll just set that up. So liters times moles per liter. So how many moles do we end up getting? So we got this number, so 0.002309 for moles. And so that's moles of permanganate. And so what do we do with this number now? So times it, so what do I need to multiply it by? By 5, so excellent. So they're in a 1:5 ratio. And so now just set up some sort of analysis. So for every 1 equivalent of our permanganate, reacts with 5 of our iron 2+ species. So times 5. And so now I have this many moles of iron then. And so what's the next step? So convert to grams. So what's the mass of iron? 55.85. So grams per mole times 55. And so I get this many grams then of iron. So I see some nods from people. And then the last step, well, we started with a 2.5 gram sample. So we want to know percentage. So divide that by 2.5. And so we get about a 25% or 26% mass percentage of iron.
What's that thing on the bottom of the .644?
This is just how many grams. So grams of iron in sample. Questions on this one? Oh, sorry. So I did not mean to pick the same reaction as was on your homework, but same reaction as before, so you can start looking at 7. And so try it on your own, see if you can do all the math, follow all the steps, and then we'll go.
So, I don't understand where the .0115 moles came from. Did we just calculate that from grams?
So we were here, the 0.002305.
Yeah.
Then we said they were in a 5-to-1 ratio.
5 to 1, okay, so divided by 5 then.
Multiply by 5. So for every one, that's why I set it up dimensional analysis. So for every one equivalent of the permanganate, it's 5, so then multiply.
By the way, do you have my email with take-home quiz?
Yeah, do you have the paper copy of it?
Yeah, I'll just not.
Okay, I prefer a paper copy so I can read it.
Yeah, I just wanted to make sure that you had something before class in case, you know. that
Yeah,
would be
no, I
valuable.
understand. I just prefer paper.
45 grams. Okay, so 45 grams sample here. Zero point zero 0.0525 liters. Okay. Multiplied by 0.05032. Is that right? No. Moles per liter. Times calculator.
So let's hear what we have. So what do we do? Yeah, go for it.
Like the first problem we need to first convert the moles of Na to S2O3 into moles, so we can stoichiometry it. It has a 2-to-1 ratio with the ozone. And then after that, we're going to take the moles of ozone and convert it to grams, and then divide the amount of grams we have by the total grams of air, and then we'll have our mass percentage.
Excellent. So I was trying to write all that, so moles, then divide by 2, and then that equals ozone still, so I could do this. And then times it by mass of ozone. So something like that. I'll just try to, so this gives you moles of. That convert to moles of iodide. So let's see what we get when we plug this all in. Sorry, trying to. So I got this for the grams. So I see some nods. So I'm just going to write this number down. So 0.001836, I guess, grams of ozone. And then the last bit, so what's the mass percentage? So then we just have to take this number and divide it by, so we have 45 gram sample. To get our percent. And so again, I expect a small number, so I get like 0.004% roughly. Excellent. All right. Any other questions on the chapter today? All right, sounds good. So make sure that the take-home quizzes make their way to me. I haven't graded them since I only have a small pile. I see some more have made their way. And then we'll take our 10-minute break and take our quiz, and I try to keep it easy for the last chapter. But yeah, we'll do our quiz in 10 minutes. Then I'm going to go ahead and end the stream.